Probably I have to agree with it. Yes. 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 Okay. So welcome everybody to our meetings concerning functional analysis, and we start with some kind of motivation. Well, this motivation is motivated by some feedback of some of you. So let us discuss what we are going to discuss during this lecture course. So first, what I want to stress is that functional analysis is the basis and actually the language of modern analysis. And modern analysis includes theory of partial differential equations, calculus of variations, infinite dimensional analysis, stochastic analysis, analytical methods of data science, and also quantum physics. So this language is important. So let us give just a very few amount of examples. And the first example will be concerning the theory of partial differential equations. So how functional analysis is used in this theory. So since Newton, mankind has come to realize that the laws of physics are always expressed in the language of differential equations. So there are three most basic equations, the most classical and basic equations, and they are Poisson equation, heat equation, and wave equation. So what is it all about? So we have a domain D in Rn. You may think n is equal to 3 or 2. So we consider some physical process in this domain D. And Poisson equation describes many different things, but in particular, potential field caused by a given electric charge or mass density distribution. So it is electrostatic. So, and this Poisson equation looks like this. So everything happens in this domain D. We have unknown function u, which describes this potential field. And this u satisfies this equation. So the sum of second order partial derivatives of this function u is equal to some known function f. So there is no time, and this type of equations describe, so to say, static or stationary physical phenomena. Another equation is heat equation, which describes, for example, the distribution of heat in a given region over time. So again, everything happens in this region D. But now there is time, and this equation looks like this. So we have unknown function u. This u now depends on time and space variables, which this function u describes the distribution of heat. And the equation looks as follows. So the first derivative with respect to time of this unknown function u is equal to the sum of second order derivatives with respect to space. And there is also some parameter in this equation. So, and the third equation is the wave equation, which describes waves, or in particular water waves, sound waves, seismic waves, electromagnetic waves, including light waves. And it looks like this, so almost like the heat equation, but instead of the first order derivative with respect to time, we have second order derivative with respect to time. And the right-hand side is exactly the same here and here and here. Also, similar expression. Okay, but actually such type of equations may have infinitely many solutions. So in order to describe some particular physical phenomena, one needs not only equation, but some more. So people speak about well-posed problems. So well-posed problems, it is equation and more information. So for example, boundary condition, which describe the behavior of the unknown function on the boundary of the domain where everything happens. And also initial conditions, that is the behavior of the unknown function u at the initial time. So what does mean well-posed problem? This means that this problem has a solution, so the solution exists. The solution is unique in some class, in some sense. And the solution behaves nicely, let's say continuous, depends continuously on the data of the problem, in particular boundary conditions or initial conditions, etc., etc. So examples of such well-posed problems are, for example, Dirichlet problem for Poisson equation. So we have Poisson equation in the domain D and some boundary conditions. Of course, just writing this, I cannot say that this problem is well posed. It depends on the right-hand side, boundary conditions, and on the domain D itself, so how nice the boundary is. But still, under some sufficiently mild assumptions, such type of problems are well posed. Another example is Cauchy-Dirichlet problem for heat equation. So now there are known U depends on space and time variables. So equation again in the domain, time is positive. And then we have boundary conditions. So for all time, we fix the behavior of our function at the boundary. And also initial conditions. That is, for the whole space, so for the whole domain in the space, but in the initial time, so time equal to 0, we control, or we fix the behavior of our unknown function. And again, depending on this phi, on this u0, on the how nice the boundary is, one can obtain a big class of well-posed problems. So yeah, so hopefully you have an impression that there are many sufficiently important equations, and it would be nice to be able to solve them. So question how to solve such problems. And of course, we pursue the functional analytical point of view. And this point of view is as follows. So we consider the unknown function u and also other ingredients of these well-posed problems as elements of some vector space. Elements, that is vectors, of some vector space. This means that this vector space is a space of functions, and hence, naturally, usually, it is an infinite dimensional space. So this is, well, the first step into the infinite dimensional setting. So we live in an infinite dimensional vector space. Next step, we consider this thing. It is considered as a linear operator acting in this space U. This operator is not necessarily defined on the whole space. Then there is a domain of definition of this operator. And naturally, this domain is the set of all elements of our vector space such that they satisfy the needed conditions, boundary conditions, and such that after application of our operator to this vector, we are still in the same vector space. So we consider vector spaces infinite dimensional. We consider linear operators acting in this infinite dimensional space. And then our partial differential equations look as follows in this setting. So this is the Poisson equation. So Laplace U, so this operator is called Laplacian, Laplace operator. So this equation is Laplace U is equal to F. This is the Poisson equation, and this is the heat equation. So even the Cauchy problem for the heat equation. So du over dt is equal to Laplacian u. So you may think actually that u is, so u is a vector in the space. Space is a space of functions, infinite dimensional, but okay. Here, this is a kind of linear equation, like you see, it looks very similar to what we see in linear algebra. And here we have something which looks like ordinary differential equation. Cauchy problem for ordinary differential equation, but well, in infinite dimensional setting. So how to solve this? So question is, can we proceed as in linear algebra and in finite dimensional analysis? What I mean by saying this. So can we do something like this? So can we just invert this operator like a matrix in linear algebra? If yes, then this is the way how to solve the equation. And in this case, if we can consider it just as ODE, ordinary differential equation in infinite dimensional setting, so then it looks like one dimension, so first order linear ordinary differential equations, so Cauchy problem. So in the course of ordinary differential equations, you know that the solution of this type of ODE should look like this. So the question is, can we proceed in this way again? So we have this partial differential equation. We consider it as infinite dimensional ODE and solve it like ODE, like this. Then the question is, these objects, what they are, what is this Laplacian to the power minus 1, and e to the power t Laplacian. So what we see here, it is actually functions of operators. So the question is how to make this functional calculus. Can we define these functions of operators? Can we use them to solve such equations? So this is like a first approach and first question. So we are interested in operators, linear operators like Laplacian, and it would be nice to have a kind of calculus to define functions of operators. Okay, second approach, even easier. So the question is, can we construct an orthonormal basis in our vector space U, like in linear algebra? Assume yes. Then, of course, okay, if our space is infinite dimensional, then our orthonormal basis should be also infinite. Okay, we hope that at least it is countably infinite. Okay, assume that we can find such an orthonormal basis in our vector space. The next step, what would be our dream? So assume we have an orthonormal basis. We decompose our unknown function u using this basis. So we have this representation with some unknown coefficients, of course. But then we apply the Laplace operator to this u, and Laplacian is a linear operator. So you may interchange Laplacian with this sum and with this multiplication with constants. So Laplacian u, having u like this, should look something like this. And this means that actually if we know how the Laplace operator acts on all vectors of orthonormal basis, we, in a sense, we know how acts the operator. Okay, so next step. So if we have this representation for any u, roughly speaking, with such coordinates ck, then we can consider Laplacian as a kind of infinite dimensional matrix with columns Laplacian ek. So it's a kind of infinite dimensional analog of linear algebra. So we associate with the Laplacian, okay, with an operator in a fixed basis, orthonormal basis, a kind of infinite dimensional matrix with such columns. Okay, and then natural question arises. Yeah, first of all, look that we have series everywhere. So k is so the sum is not finite. So the question is, yeah, what about the convergence? If everything is fine here, so can we guarantee the convergence of all the series? But it's a small technical question, of course. But principal question, so what to do further? So if we have an orthonormal basis, we have a linear operator delta, which acts like this on vectors of this form. Then next step, can we diagonalize such a matrix? That is, can we guarantee that there exists an orthonormal basis of eigenvectors of this operator? That is, can we construct such orthonormal basis that the operator applied to these vectors just these vectors themselves multiplied with some constants, eigen values? If yes, then we can really proceed as in linear algebra. That is, Laplacian u is this sum. And then in the case of Poisson equation, it was like this. So we decompose u using this O and B, and we also decompose the right-hand side using this O and B, orthonormal basis. Hence, we obtain, so this is the Poisson equation. Okay, Laplace u is equal to f. This is my f. And so we have this identity. And from this identity, you can see immediately that ck lambda k is equal to fk. Fk is known, lambda k is known via Laplacian, so you can find ck. If you find ck, you find u. So you solve the Poisson equation. So yeah, conclusion. It would be totally perfect if we can construct orthonormal basis, if we can have a lot of eigenvectors of our operators, then everything is very easy. So conclusion, So we need to develop analogs of linear algebra and finite dimensional analysis, but on infinite dimensional spaces. And we are particularly interested in the theory of linear operators, thinking about Laplacian, acting in infinite dimensional vector spaces. So this is a message from theory of partial differential equations, what would be nice to have in functional analysis. Probably a couple of comments here. Of course, not in all spaces we can find orthonormal basis. Yeah, and also not all operators have this nice property. But still, there are some ways to generalize it and to survive, even if our dream is not true. But still, there are some ways to solve the equations. Okay, but we are not going to go further, and this was just a message what would be interesting for us if we are thinking about theory of partial differential equations. Okay, then a few words about stochastics, stochastic processes, stochastic analysis. Again, just a simple example. So first of all, what is a stochastic process in continuous time? It's just a family of random variables. All random variables are defined on the same probability space. And this family is parameterized by some parameter t lying in this segment, so in this interval, and this t plays the role of time. Okay, basic example is the Wiener process. Mathematicians also call it Brownian motion. So this is a process. I just recall that this is a centered process with continuous paths, stationary and independent increments, starts at zero, and increments, they are Gaussian with zero mean and this variance. Okay, so this is how a path of Brownian motion looks like. So assume we consider some interesting stochastic process. And if this process has continuous paths, so the whole process x can be considered as a single random variable x, taking values not in R anymore, but in the space of paths, so to say, the space of continuous functions defined on this interval. So this is an infinite dimensional space. And so a stochastic process is a kind of infinite dimensional random variable. So if you want to do probability theory with infinite dimensional random variables, yeah, you need infinite dimensional setting and hence functional analysis. Okay, assume we observe the underlying interesting process x at discrete time points with time interval 1 over n between observations. So this is a picture. Let me make it bigger. So I have drawn this time scale, and so these are the points of observations. So there is 1 over n between observations, and each observation gives us a corresponding point here. So this process of observations gives rise to some simpler stochastic processes, namely stochastic processes which do not change between observations. So we have something during the observation, and then nothing change up to next observation. Then again something, some random variable, and then nothing changes. So obviously the paths of these processes are simpler, and obviously these simple processes are easier to investigate and make some conclusions about their properties, but we are actually interested in the underlying process X. So natural question is, do these simple processes really approximate the original underlying process X? What does mean approximate? This means that they should converge to X in some sense, somewhere. So we need some spaces and we need a kind of convergence in these spaces. So if you want to approximate stochastic processes by some nicer processes, yes, again, you need a kind of convergence somewhere in infinite dimensional setting. And so conclusion, it is interesting to investigate infinite dimensional spaces and the notions on convergence there. Okay, one more example from stochastic analysis of financial mathematics in continuous time. So there are the so-called Black-Scholes type models. These are mathematical models for the dynamics of financial market or stocks in financial markets containing derivative investment instruments. So in the frame of Black-Scholes type models, the price of a market stock is given by a stochastic process, and this is how this process looks like. So the process is given explicitly, but with unknown parameters, mu and sigma. And these parameters play the following role. So mu is the average interest rate, and sigma is the volatility of the market stock or asset S. And so W is the Wiener process. And in this setting, this mu and this sigma, they are themselves, they are stochastic processes. And the Wiener process is, of course, also a stochastic process. So we have this expression. And actually, this expression is a solution of the following stochastic differential equation. Okay, so what you see here in this expression and here. So here you have integral with respect to ds, so Lebesgue integral here as well. So if the processes have sufficient mu and sigma square have sufficiently reasonable paths, I mean the smoothness or continuity, yeah, if the paths are continuous, then one can define such integrals pathwise, and it's okay. But what is this? What does mean this object, and what does mean this object? So this is, yeah, the counterparts. So stochastic integral, stochastic differential. And coming back to Brownian motion, you see how it looks like. So actually, one can prove that the paths are not smooth. They are not differentiable. They are nowhere differentiable. So this means that we cannot understand this differential in the sense of analysis one, so to say. Yeah. So one needs an advanced calculus. So the question is, yeah, what are these objects? Stochastic integral, stochastic differential. And yes, so there are answers. In particular, one can define these objects in the frame of Ito calculus. But what does mean Ito calculus? This means that we define stochastic integral for simple integrands, and then we make a kind of extension procedure. And for this extension procedure, we need the so-called Ito isometry. And isometry, it is a particular type of mapping between particular spaces, of course, infinite dimensional spaces. So again, there are mappings in infinite dimensional spaces, and this is functional analysis. And Ito calculus and also Malevin calculus and stochastic analysis itself is, in general, it's a kind of infinite dimensional analysis, or analysis in infinite dimensional setting, different versions of analysis in infinite dimensional setting. So consider all this as a kind of advertisement. So finally, the conclusion after this motivation. So we need to study properties of infinite dimensional spaces, in particular the notions of convergence in such spaces. This is like a first aim of this lecture course. And we need to study properties of linear operators in infinite dimensional vector spaces. This is the kind of second aim of our lectures. Okay. And this is the program. I have already announced this program, so let us see if we succeed to cover all what I want, so to say. But it depends also on you. So let us try. And concerning the literature, so the main literature is the book of Bogachev and Smolyanov, Real and Functional Analysis. It is available both on Russian and English. And also there is a book, Kolmogorov-Fomin. It's a classical book, already quite old one. It is also available in Russian and English. In Russian, it is a unique book. In English, it is a two-volume book. So I will focus on, so I will use these books mainly, but there is also a list of like a classical books or just very good books on functional analysis. And some of them are also available in Russian. not only in English. So Yoshida functional analysis, Brezi's functional analysis, Sobolev spaces and partial differential equations, Lux functional analysis, Conway, A Course in Functional Analysis, Danford Schwartz, it's a classical book, 3 volumes on linear operators. It's a kind of a book which contains everything. It's a fundamental treatise. And also Naimark, linear differential operators. In Russian, it is 1 book. In English, it is 2 parts. Okay, so these are, I guess, everything concerning the introduction and motivation. And now a good time to have questions if there are any. Okay, then I have a question. If so, I'm too fast or not?
Everything is okay.
Okay, good. Uh-huh. Okay, so please, if I'm going to be too fast, interrupt me and ask questions or ask me to repeat or whatever. Please control me because, yeah, who
It was
knows?
a very nice introduction, and I think many of us are into stochastic analysis, so
Yes,
it
yes.
will be pretty helpful. Yeah, maybe for
Okay.
the actual material. If it will be too fast, we will let you know.
Okay. Well, I didn't know if so. What are your preliminary knowledge in stochastics? So probably you know everything what I have already presented. Probably no. Okay, anyway, so this is like a motivation that we need spaces, convergence, vector spaces, linear operators on them and their properties. Okay, good. Then we start with chapter 1. And chapter 1 is topological spaces. And this week is devoted to topological spaces. And yeah, again, we start with a kind of, not a motivation, but um, or a motivation. So usually people, when they start with analysis, not with functional analysis, but just with analysis, they first do this analysis in R and then in Rn. And then at the end of lectures, there are a kind of chapter about metric spaces. So I assume that you know something about metric spaces. So is it true or not?
Yes.
Yes.
So okay, at least 2 people know something about metric spaces because I will refer to them from time to time, but at the moment we will recapitulate some things related to metric spaces before we start the general theory. Okay, so topological spaces, chapter 1. And recall what we had in a metric in the setting of metric spaces. So if you don't know what is it, you may always think about Rn, and the metric is just a distance in this space. So I recall the definition. So a metric space is just a pair X and D, where X is just a set. Of course, the interesting situation is when X is not an empty set. It is assumed usually. And there is a mapping D. So it has 2 variables. So defined on so D is its domain is X times X, and its values are non-negative. So this is the mapping such that D. So once again, so this mapping plays the role of a distance. That's why it is denoted as D. So distance between X and Y is equal to 0 if and only if X is equal to Y. Distance from X to Y is the same as distance from Y to X for all elements X and Y in our space X. So this is the symmetry of metric. And distance between 2 points X and Z is smaller or equal than the distance between X and some other point Y plus the distance from Y to Z. And this also holds for all elements X, Y, Z in our space. And this is a triangle inequality that X, Y, Z. So distance between 2 points is not bigger than if we make in German Umleitung. So if we first visit some other point Y and then go to Z, not directly from X, but with some extra stops, extra visits somewhere else. Okay, so this D is called metric or distance function. What else? So if we have distance, we may define open balls. So an open ball will be denoted like this, and this is an open ball with a centrum in x0 and radius r. So it's just all the set of all points in our space X such that the distance between X and X0 is strictly smaller than R. Okay, we have distance. We define open balls. Having open balls, we may use them as neighborhoods of points. Yeah, so an open ball with centrum in x0 and radius epsilon will be called epsilon neighborhood or open epsilon neighborhood of a point x0. Having neighborhoods, we may define the convergence. Convergence, this is the basic, the fundamental operation of analysis. So if at school in algebra, so to say, we consider addition, multiplication, yeah, such operation, then in analysis, or roughly speaking, topology, convergence or passing to the limit, yeah, this is the fundamental operation. As soon as we have the notion of convergence, we may do all other things. So the whole analysis. Having convergence, we may define what is continuous, what is differentiable if we want, or integrable. Yeah, so all the things, or depending on the spaces, of course. But but all the things in analysis, they are based on the notion of convergence. So you see, in the setting of metric spaces, we have distance. This gives rise to neighborhoods. This gives rise to convergence, and we are done. We are able to do everything. Let me recall you what is the convergence. Definition. A sequence xn converges to a point x. Everything happens in our metric space x. If for any epsilon positive, there exists a natural number n. This n depends, of course, on epsilon we choose, such that for all indices n, small n, not smaller than this big N, we have the following. The distance between xn and x is smaller than epsilon. What does this mean? This means that the whole tail of our sequence, starting from some number, the whole tail, the rest of the sequence lives in epsilon neighborhood of this point x. Yeah? So instead of writing this, we can write this, and the convergence is defined only in the terminology of neighborhoods. And also what is important here, so why we use this as a definition of convergence. So we have any epsilon. This means that if we have a point x, we may consider different neighborhoods in particular. What is interesting for us, we may consider arbitrary small epsilon, so the smaller and smaller and smaller. So from this definition follows that we can actually construct a sequence of neighborhoods of balls so that they are so that they contract to the point x. So a sequence, so a countable set of neighborhoods such that they are getting smaller, smaller, and smaller, and they, so to say, contract to the point x. Okay? So this is the idea of this definition, and I hope that it is obvious for you because analysis one is already discussed. Okay. Moreover, open balls are basic building blocks for open sets. So I recall you that a set U in a metric space is called open if it contains each point with some neighborhood. That is, for any point x in this set U, there exists some epsilon, which depends on this point x, of course, some positive epsilon, such that the whole neighborhood of x with radius epsilon lives in this set U. That is, U contains each point with some neighborhood. This means actually that we can represent this space U in this way. So this is the union. We take the union over all points in our set, and each point is actually surrounded by a neighborhood with some radius, which is totally in U. So is this identity clear, or should we discuss it in more details?
No, this
It's clear for me.
Okay, for the others?
Yes,
For me too.
Okay, so let us go further. Well, yeah, so this is a convention that empty set and the whole space X, they are open. Let us recall it. And also let us recall the following properties of open sets. So there will be some exercises. We are not going to make them during the lectures, but you are strongly recommended to do it yourself at home. So the properties of open sets. So let us have a metric space, and then a union of arbitrary many open sets is an open set. And intersection of finitely many open sets is also open. And this is a kind of very important properties of open sets. So are they known, obvious for you, or there are some questions concerning this?
so I remember doing such exercises. Yeah, I think I can do this.
Okay,
Me too.
yes, try to do it. So try to
Yeah,
write down a rigorous proof of these statements. Okay, everything is very simple, but it's very instructive to write rigorous proofs of simple things.
sure.
Okay, so this is what we have in metric space settings. And remark. So first of all, one can actually use just open sets instead of epsilon neighborhoods in the definition of convergence. Yeah, so if we have a point X, we don't need only circles. We can have something like this. Yeah. So the idea is again that we can find at least a sequence of neighborhoods which contract to the point which we are interested in. Okay, so yeah, so in this definition, yeah, instead of writing this, we can just use a neighborhood. That is, for any neighborhood, there exists a number such that the whole tail of a sequence lives in this neighborhood of the interesting point X. Okay, so this is just one remark, but on the other hand, this remark may help us in the case when we do not have a distance function. So sometimes we need to live in the spaces where there is no metric. There is no this D starting from which we can go to convergence and make analysis. So what we do further, we discuss general theory of topological spaces where we probably do not have a metric, but we want to make an analysis as well. We don't have open balls if we don't have metrics, but we can create open sets. And then this will be enough for making the whole analysis. Okay, so now the kernel things. So topological spaces, general theory, and we start with definition 1.1. So let us write it. So we will define what is a topological space. So let X be a set a system which is denoted by tau, a system tau of subsets, of subsets of X is called topology. And this is the object we are interested in, topology. So the first requirement is that the empty set and the whole space X, the whole set X, they are elements of our system tau. Second property, that for any two elements, A and B, of our system tau, we have that their intersection is an element of tau. And the third property is that for any family, a lambda, so lambda is a parameter, it belongs to some parameter set, big lambda. And this big lambda may be arbitrarily large, probably uncountable. So we have a family of such elements and they all are elements of our system tau. So for any such family, we have that the union of a lambda is a lambda. This is again an element in our system tau. That is, these properties are exactly properties of open sets. So these two sets are considered as open by convention. For any two open sets, their intersection is open. And if for any two, then for any finitely many as well, of course. So finitely many, so intersection of finitely many open sets is open, and union of arbitrary many open sets is open. The elements, the elements of the system tau are called open sets. Or probably sometimes when we want to stress that it happens in this topology tau, we call it tau open sets. And a pair X and tau is called topological space. So once again, in the case of metric space, we first have metric, then we have balls, and starting with open balls, we create open sets. And notice that they have these properties. In the general situation, we just take any system of sets we want, but such that these properties are satisfied. And we call this system of sets open sets. And that's it. So we don't have balls, we're not able to construct them probably, but we just choose ourselves, arbitrarily, roughly speaking, as we want, any system of sets which satisfy these properties. And that's it. This will be our topology, and then we will do analysis based on the chosen topology. Example, of course. So are you finished with writing my notes?
Yes.
Yes.
For 1 second.
Yes, yes. Okay. I guess a second is already
Yeah, thanks.
done, and we can go further. So this is a definition. Now you have it with you, and we make an example. Okay, so example of topological spaces. So first example is just tau consists only two sets, empty set and X. This is the so-called trivial topology. I hope it is obvious that all assumptions of definition are satisfied. Yeah. Okay, second example. That tau is just equal to, so in Germany it is denoted as P of X and it is called Potenzmenge. That is, and also there is this notation, and this is just the set of the set of all subsets. The set of all subsets of X. This is called the discrete topology. On X. Okay, of course, these two topologies are not that interesting, but sometimes they are used for examples and counterexamples. So, third example. So let X and tau be already be a topological space. And let we have a subset X0, a subset of X. So consider the following set. Tau 0. This is defined as follows. It contains intersections U intersected with X0 for all U elements of tau. That is, we consider all open sets in X and intersect them with X0. Then this X0 with this system tau 0 is again a topological space. And again, it is an exercise for you to check that this system really a topology. That is, this system satisfies all the assumptions in the definition 1. And this tau 0 is called the induced topology, or topology induced from X. Okay, example number 4. Okay, let XD be a metric space. Then the family of sets which are open with respect to D, that is, which are open in the setting of metric spaces. That is, it's a union of balls, open balls. Yeah, so the family of sets which are open with respect to D is a topology which is called topology generated by the metric. Topology generated by the metric. That is, all metric spaces are examples of topological spaces. By the way, can you give me some examples of metric spaces except R and Rn? except R and Rn. Do you know some other metric spaces? Just any?
Well, space of continuous functions on
Yes.
A with the supremum norm.
Yes, yes, for example, yeah. Some further examples?
Discrete metric on any space.
I hear you very bad.
Discrete metric on any set.
Okay, yes, why not? Okay, yes, of course, yes. So standard spaces of functions, they are usually metric spaces, yeah, like LP spaces, continuous functions, bounded and continuous functions, or Borel measurable functions. Again, with a suitable supremum norm or P norm, yeah. Okay. But also in Rn, if we consider, for example, yeah, a circle in R2, yeah, it's a nice metric space. Not a vector space, but a metric space, yeah. So like a manifold in Rn is also an example. Okay, so metric spaces is a special case of topological spaces. And remark concerning this. So a topological space is called metrizable if there exists a metric on this space X such that the topology induced by this metric D coincides with the chosen topology tau. That is, all open sets which are contained here are really the same as open sets induced by the metric. Be careful, however. So each metric induces a topology. That is, each metric allows us to construct open balls. Open balls allow us to construct open sets, and they are a nice topology. So each metric induces a topology. However, different metrics may induce the same topology. So if we are already here, so if we start with a set and topology, starting with a metrizable topology, we cannot restore the unique inducing metric. So we cannot restore the inducing metric in a unique way. And an exercise, let us consider these two metric spaces. So R with two different metrics. This is one metric, and this is another metric. So actually show that these two metrics induce the same topology. That is, open sets, which are open with respect to this metric, they are also open with respect to this metric, and vice versa. So this is a home task for you. Okay, we go further. Remark 4. So given a topological space, we define what is called a base or a basis. A base or basis for the topology tau is a family, so subfamily, subsystem of elements of tau, such that every open set of the topology tau can be represented as the union of some elements of beta. These elements of beta are called basic open sets. So in metric spaces, basic open sets are open balls because all open sets can be represented as union of open balls, which we have already seen, yeah, today. So U was a union of B epsilon of XX, and union is over all X in U. So this is exactly the representation. So open balls are basic open sets in metric spaces, but in topological spaces, we can choose different families, yeah, of this type. And this thing, so base is a family, so subfamily, such that every open set, so every element of topology tau can be represented as the union of some elements of beta. So this statement is equivalent to the following statement. So a family beta is a base if and only if, of course, it's a subsystem of open sets. And for every open set U in tau and any point X in U, there is some basic open set B such that X lives in B and B is a subset of U. What I mean, so we take any open ball, we take any open set, like in a metric space. We are interested in a point X, so this is a point we are looking for. And we take any open set which contains X, and we consider this open set as a neighborhood, open neighborhood of X. And instead of this open set, we can just take an open ball, which is contained in this neighborhood. So this is the reason why we don't need all open sets, and it is enough for us to consider only open balls in the setting of metric spaces. Okay, so these two statements are equivalent. So let me the family such that this happens, and this is the family such that this happens. So this is exercise for you to show that these two things are equivalent. These two formulations are equivalent. Is it obvious for you at the moment or not?
Excuse me,
Yes.
but if we consider, for example, trivial topology, I suppose for the first your definition, the base for it would be the whole space and empty set, but for the second definition, I think it's not true because we shouldn't cover any point.
Why? So if we consider this topology, let me write it down in a clear way. So this is my tau. Then as beta, we can take only tau itself. So then
Yes.
yes.
Okay. Yes. Because every point covered by X. Okay, sorry.
Yeah, so not any subfamily is a base, but base is a subfamily which satisfies either this or sorry. So either this statement, this requirement, or this requirement. Yeah. So if we consider such topology, then the only base is the topology itself. But my question was that there are two formulations and they are actually equivalent. But this is an exercise for you. Let's do it at home. Again, everything is very simple, but write down a rigorous proof that these two things are equivalent. Okay, and again, so having this definition, take in mind open balls in the setting of metric spaces. Okay, let us go further. Is it clear here? Can we go further?
Yes.
Okay. Yeah, example, a collection of open balls in a metric space is a base of the topology induced by metric. Further, if we consider the particular metric space, for example, R with this topology induced by this metric, then as basis we can take all open intervals. These are open balls in this metric space. But we also can take, for example, all open intervals with rational endpoints. So it's a countable base. And still it is a base. That is, for each point, we can always construct, and for any open set which contains this point, we can always construct a ball. So in R, this is an interval. In Rn, it should be a ball with a rational radius. Okay, and take it as a base. Okay, so let us go further. Now definition 1.5. So like a first item in this definition. Any open set or let X belong to X. So we fix some point. We are interested in this point. Any open set U containing X is called a neighborhood or an open. We will consider only open neighborhoods. That's why I write it in brackets. So a neighborhood. Of X. Notation UX. UX means that U is an open set which contains X, so I consider it as a neighborhood of this point X. And then I define the notion of convergence. So a sequence Xn of elements in our space X. We are now living in topological spaces. X tau. A sequence Xn in X converges to X, an element of our space, if for any neighborhood, we consider only open neighborhood Ux of X, there exists a number, a natural number, which of course depends on the choice of our neighborhood, and this is natural number such that Xn belongs to this neighborhood for all indices n bigger or equal to this big N. So I hope you see that this is exactly this definition looks exactly similar as in the case of metric spaces, but instead of open balls, we consider neighborhoods, open neighborhoods. And now there are many funny things because everything is very general. So everything depends on topology, how good our topology is. So in the case of metric spaces, I said that in our definition allows us to, if we have a point X, our definition allows us to have like a concentrated sequence of concentrated neighborhoods which contract to the point of interest. But now, do we have the same here? The statement is that for any neighborhood, everything is fine. But now the properties of this convergence depend on how many open sets we have, actually. So remark, caution. Generally, a limit of sequence in a topological space does not need to be unique. Example, let us consider topological space with this trivial topology. Then each sequence of elements xn in this space converges, so a sequence converges to any element x in x. Do you see? What is the problem? For example, we have x and we have a sequence xn. I don't know, xn. To show that x is the limit of xn, we should show that at least a tail of xn is contained in an arbitrary open neighborhood of x, but there is only one neighborhood of x, the whole space. That is, each sequence completely is contained in this neighborhood of x, and this holds for any point x. Yeah. So each sequence converges everywhere, I mean, to all points x. And this is a kind of situation where the analysis is not really interesting. So what is missing? The missing point is that there are not enough open sets. So if there would be some open sets, like open set which is a neighborhood of x, which does not contain this sequence, or okay, so the idea is that in order to have a unique limit, we should be able to separate points. That is, if we have 2 points which can be candidates for limits, yeah, we should also have open sets which separate these points. Yeah. So it's not interesting to consider just arbitrary topology. Topology should be good enough, that is big enough, and this gives rise to the following definition. So, conclusion, there should be sufficiently many open sets which allow us to distinguish the points for the uniqueness of limits. And this gives rise to the definition 1.7. A topological space X tau is called Hausdorff So this is the notion Hausdorff space, or Hausdorff. If for any 2 points, x and y, 2 points in our space, which are distinct, so they are not equal, there exists disjunct, disjoint open neighborhoods. We consider only open, but in principle, one can consider as neighborhood any set, not necessarily open set, any set such that the point x is in the interior of the set, and then analysis will be the same. But we consider only open for the simplicity, so to say. So there exist disjoint open neighborhoods. Ux is a neighborhood of x, and uy is a neighborhood of y. This is a separation axiom with number T2. So people say that we have Hausdorff space or space which satisfies separation axiom T2. And of course, so there are different options how to separate points. And there are different separation axioms, but they lead to different types of analysis, depending, so the properties will be different when we consider topological spaces with different separation axioms. But Hausdorff spaces is a kind of gold standard, so this is in a sense, the optimal choice of separation axiom. So we have 2 points, we can separate them by open sets which do not intersect. Okay. So then, if you are finished with writing, we can go to examples. Probably let me write down the remark. The limit of a sequence, if exists, is unique in a Hausdorff space. And this is a kind of, again, exercise for you. But so the principle is as in analysis 1. If there are 2 limits, then we can separate them by open sets. So, okay. So examples. May I go further?
Yes.
Yeah.
Okay. I don't remember if I have it in a written form. No, I guess I don't have it in a written form. So example, example 1.8. So first part of example, let us consider X, so this is a set. The set contains 2 points, X and Y. And let us consider the following topology. This topology contains empty set, 1 point set X, and the whole set big X. Then, so this space, my question to you, is this space Hausdorff or not?
It doesn't contain a set. This topology doesn't contain a set, a neighborhood of Y that doesn't contain X.
Yes, that's why the conclusion is
Not Hausdorff.
not Hausdorff. Okay, this space is called Sierpinski space. Just a keyword. Okay, so second example. Well, so if we have a metric space, something goes wrong. Yeah, if we have a metric space, is it a Hausdorff space or not?
Yes.
Yes.
Yes. Yes, so if we have 2 points which are different, then we have a distance between them. So there is a distance. We can take d half, and then we can take 2 open balls open, yeah, which do not intersect and have radius d half. So d is the distance between x and y. So this is how we separated the points. Okay, so let us go further. So as I said, if we have convergence, if we have topology, it's enough to define convergence, and it's enough to make the whole analysis. So what's going on further? We will just consider some standard definitions which are known for you from the setting of metric spaces, but now we just reformulate them in the general setting of topological spaces. Everything happens sufficiently in a similar way. That's why it is on slides. We're not writing it anymore, but there are still, at each point, there are some question marks. So let us start and discuss what we have. So we will be in the setting of Hausdorff space. So this is the most pleasant setting, and we don't need further generalizations actually for the subsequent theory. So we have a Hausdorff space, and we have a set of this in this space, and we have a point in this space. So this a point X is called a limit point or accumulation point of a set A if each neighborhood, we consider only open, if each neighborhood of this point X contains at least one point of A other than X itself. Okay, this is a known object, a known notion in the theory of metric spaces.
I think it's like the more familiar version of it is that neighborhood contains infinitely many points. So
We
this is a
we will discuss it in a second. Yeah. This is true, but only in Hausdorff spaces, not in general setting. But nevertheless. Okay, so hopefully this notion is clear. Exercise, the following is true in Hausdorff space. X is a limit point of A if and only if each open neighborhood of X contains infinitely many points of A. Yeah? Exercise. So is it clear? Should we discuss this exercise or make it as a home task?
It is clear.
I don't understand. To speak louder.
It is clear for me.
Okay.
well, we can use the axiom of Hausdorff space and
Yes.
each time take a different point and
Yes.
construct a sequence of construct an infinite sequence of points.
Yeah. Exactly. Okay. Good. Let us go further. Caution. If X is a limit point of A, it does not follow in general, then that there exists a sequence in this set A such that X is the limit point of the sequence. So be careful. In general setting, a limit point or accumulation point of a set, okay, a set can be just a sequence, yeah? So I can consider as a set just a countable set of different points. And then there will be a limit of a sequence, yeah? But in general, if we have just a set and a point which satisfies these assumptions, it does not follow that we can construct a sequence such that this is the limit of the sequence. So what is the problem? Because so of course we can do it in metric space. How we do it in metric space? So we have X. We take any neighborhood of X. It contains a point. Okay, let me assume that everything here is the set A. Okay, so we take a neighborhood. Since X is a limit point of A, then this arbitrary neighborhood should contain a point which is not X but belongs to A. We take a point. Then we separate these 2 points, X and this one, and we construct a next neighborhood which does not contain this point. Yeah, and then we iterate the process and we have a sequence. Yes, like a sequence of neighborhoods which contract to the point X. Yeah, this happens in the metric space. But in the general setting of Hausdorff space, it may happen that in order to contract to X, it is not enough to have just a countable sequence of neighborhoods. We will see such example at the next lecture. So sometimes in order to, so to say, really to contract to the point, we have to not to go like this, but we have to go like uncountably, yeah? Transfinite induction, yeah? So not in a countable way. In this case, you cannot create, sometimes you cannot create a sequence which converges to X, even though this holds. That is, for any neighborhood, it's fine. But in order to really to go to the limit, you have to use uncountably many neighborhoods, so to say. Okay, probably it looks quite unclear, but we will discuss it when we consider a particular example. But of course, everything is fine in metric space, and actually everything is fine. So there are no problems in the spaces which are, so to say, not too fat. Such not too fat spaces are the so-called Fréchet-Uresson spaces, in particular first countable spaces. So these are just keywords. Further, you can take, for example, even in Wikipedia, look at these keywords and to see further information, to get further information. But the message is as follows. You see, we start with a simple definition. Everything is similar to the metric spaces, but there are always some cautions, and one should be careful. As soon as we are in the infinite dimensional setting, anything may go wrong. Okay, so this was this first guy. I guess we have still 5 minutes to discuss a second guy. So second definition, X is an adherent point of A. In Russian, X limit point is предельная точка, limit point, accumulation point. This adherent point in Russian is точка прикосновения. So X is an adherent point of A if each open neighborhood of this point contains at least one point of A. So this requirement is dropped. Just at least one point, not necessarily different from X. So this is the difference. Exercise to make at home. For each limit point of A is simultaneously an adherent point of A. I hope it is clear from definitions. So each point which belongs to A is an adherent point of A. Each adherent point of A which does not belong to A should be a limit point of A. And there is also the notion isolated point of A. So X is an isolated point of A if X belongs to A, but is not a limit point of A. So exercise which we do right now. So we consider this space R, it's a metric space with a standard metric. And we consider this set. And I ask you to say me what are the limit points of this set, adherent points of this set, and isolated points of this set. You're welcome to start with, let's say, with limit points. We're doing all together, and you just saying me what I should write down.
Limit points is 2 and 0, 1 closed.
Yes, that's true. Let me write down it in a proper way. 0, 1 closed, union with the point 2. Is it clear for everybody? Okay, adherent points.
Oh, just A and also 1 and 2.
Yeah, that's true. Is it clear for everybody? Okay, isolated points.
So it's a sequence from
Yeah.
the right part of A.
Let me choose the color. These are just these points. Yes, okay. So I think that's enough for today. We have just 90 minutes. And at the next lecture, we continue with topological spaces. So the aim is to discuss the basic definitions and then to discuss a couple of important examples, particular examples, when we can see what may go wrong. Okay, so I stopped the recording. Let me do it. Oh yeah, let me find.